Hello everyone, my name is Russell Wu. I'm just going to carry on with the rest of the chapter. Mr. Tan has mentioned, has gone through the rest. We have piecewise function, we have periodic functions, and now it's a slightly one more concept, last one before we conclude the chapter. It is what we call parametric equations. Um, Name is one thing, but I just want all of us to look at the screen. No need to copy. I just give you a very simple example, and I think all of us should be able to get it. Now, traditionally, what we see, we always get is this kind of equation. This is what we call a Cartesian equation. Correct? Cartesian because it has y and x only. Now, how does it look like? We say, oh, okay, we sub x equals to 0, you get y equals to 0, you get 0, 0. You get x equals to 1, y equals to 1, you get 1, 1. X equals to 2, y equals to 4, you get 2, 4. Correct? You substitute in all these kind of points, and you sub in the middle points, you join them all up, you get a quadratic equation. This is what we call a Cartesian equation. I think this is what everybody is quite familiar with. Now, but there is a different kind of equation called parametric equation. Essentially is this. Now, I will define it like this. You may find it a bit odd, but never mind. Let's use x. Say x is 2t, y is 4t squared. Then you realize there's a weird looking thing called t. But essentially it works the same. Let me elaborate. If you see this one, alright, sorry. If you see y equals x squared, well, how do we get this point 0, 0? We substitute x equals to 0, then you get y equals to 0. You substitute x equals to 1, you get y equals to 1. Now I'm going to do the same thing here, except that this time I'm going to substitute t equals to 0 into here and here. So if I substitute t equals to 0 here, I get x equals to 0, y equals to 0, I get 1 point. If I sub t equals to half, alright, let's say t equals half, I get x equals to 1, yes, I get y also equals to 1, I got also another point 1, 1. This is when I substitute t equals to half. Yep. If I substitute t equals to 1, I get x equals to 2, y equals to 4, I will also get 2, 4. This is when I substitute t equals to 1. Now, of course, I substitute the in-between values, I will still get this curve, I will still get this curve. Now, what is the main difference now between this one and this one? Actually, they describe the same curve, it's just that this is defined in parametric form. That is the overview I'm going to cover. So this is not in the notes, but never mind, actually you don't need to really copy. But this is the main idea of what we call parametric equation. And with this t, you realize it's not x, it's not y, it's what we call the parameter. So let's go to the notes. The notes is a bit lengthy, but essentially it says the same thing. Just now I gave this example of x is a function of t, y is a function of t. Example. Just now I said x can be 2t, y can be 4t squared. Correct? So, then you say, oh, okay, like as I mentioned just now, t is what we call the parameter. So, as t varies, your x, you have different points x and y, and therefore it plots out a curve. Then you say, how come so troublesome? Why do we have to define a graph parametrically and not Cartesian? Because just now you say x equals t squared, y equals to t squared is so easy, so y equals x squared is so easy. This is what we call Cartesian. Why do we go through so much trouble to define it like that? I have only two answers for you. One, sometimes, alright, the t, the parameter, if you do physics, sometimes the t mean a specific quantity, which means it may mean time. That means after 1 second, the object is at this coordinate. After 2 seconds, the object is at another coordinate. The other reason why we use parametric equation is some equations cannot be defined in a Cartesian manner, in a Cartesian equation. So this is an example where this y equals x squared and this one are the same, but there are some equations that cannot be described, cannot be described in a Cartesian manner. So all these are words you can read on your own, all right? And we will go through example 9 in a bit.